And well, there are various equivalent models that we can use, but I'm going to define what's called the quantum circuit model. And the quantum circuit model is perhaps the easiest model to start with. Okay? And by the way, I think that there are not enough questions, and I'm going to run pretty fast on this because what we're doing in this intro day is essentially putting the whole intro course to quantum computation in one day. So do stop me when you want. Okay, so in order to define a computational model, I have to start with what's computation. Let's start with a classical computational model that will be simpler and then extend it. So, okay, so classical computational model, well, there are various models, and perhaps the first and most famous one is the Turing machine. And we won't be using much the Turing machine. How does this work? This is okay. So we won't be using much this Turing machine model in this school. Maybe Sandy in her mini course will use it. But let's just recall what it is, just to have it in mind. So the Turing machine has an infinite tape with letters written on this tape coming out of a finite alphabet. And there is a finite state machine here. And there is a head pointing at one location in this tape. And this thing proceeds, it starts with the head pointing at the beginning of the input written here on the tape. And then the state proceeds by the Turing machine makes one step by looking at transition function, which just looks at the state of this finite state machine and the letter currently that the head reads, and decides according to these two things, a state and a letter, what will be the new letter written here and what will be the new state, and where will the head go, to the right or to the left. And the thing is that this finite state machine has two special states, accept and reject. And when this machine reaches one of these states, it halts. And so we can talk about the language that this machine accepts. And if it holds for every x, for every input x, either in accept or in reject, then we say that the language that it accepts is the set of strings such that this Turing machine ends with accept for those x's. Okay? And we'll say that this is a language that can be decided in polynomial time if this machine holds after time, meaning number of steps, that is polynomial in the length, the number of bits of the input. Okay? So we call this P, the class P. The class of languages that can be decided like that by a polynomial time classical Turing machine. Now, this model, we can quantize it. It is possible to talk about quantum Turing machine, but it's a big headache because the tape is infinite and things look horrible. So we'd rather, it's possible, and it's known to be possible, and everything was proven, but we'd rather work with circuits. So let's look at classical circuits for a start. And this is an equivalent model. So with circuits, we have a circuit for every size of the input. So if your input is n bits, we have a circuit with n inputs here. This n will be 4 here. And each node here in this graph will be associated with a gate, not, and, or a Boolean gate. And it's local. So each gate here acts on 2, 3 bits, and that's it. And we say that this circuit computes a function f from n bits to 0, 1 if given any x from here, the output here is going to be f of x. Okay? So what would be P in the language of circuits? So here is a definition. P, we say that a language, L, is in P. That's a subset of all n-bit strings for all n. Okay? That's L. This is in P if the sizes of the circuits that decide on the characteristic function of x for a given size n if these circuits, their sizes grow polynomially with n. But let's say it more formally. If there exists a sequence of circuits, Cn from n equals 0 to infinity, and a polynomial such that the size, meaning the number of gates in Cn, is bounded from above by a polynomial, such that for all x of n bits, and for all n, if x is in the language, then the circuit outputs 1 here, and if x is not in the language, then the circuit outputs 0. Okay? So then we have a sequence of polynomial size circuits. Yes?
Do you have arbitrary fairness?
No, so it was arbitrary, but I didn't mean it to be arbitrary. Let's bound it from above by 3, okay? Or 2, you can also do 2. So in fact, all you need for classical computation is and not gates. So fan-in is 2. Fan-in is the number of wires that get into the node, and time goes upwards. Okay? So there's one thing that is a small comment that, I mean, it's a big comment, but it's very important, but not for this school. And this is the fact that these circuits, actually, if we don't restrict who designs them, they can, in themselves, hide very, very complicated, and in fact, undecidable computations. Because if, for example, we have a function that only depends on n, the size of the input, and not on the input itself, well, we can design the circuit Cn to just output this f of n. And if f of n is undecidable, then we have a sequence of circuits of even size just 1 that computes an undecidable function. So we need to add a restriction that's called uniformity that says that these circuits are somehow designed by a single Turing machine that for given n designs the description of the circuit, Cn, and that this takes polynomial time. So nothing is hidden sort of in the hard wiring of the circuit. But having said that, I just want to forget about this uniformity and will not think about it anymore. We'll just talk about polynomial sequences of polynomials growing in size circuits. Yes? Please use the mic.
I just want to ask, like, when you allow, do you put any restriction on the fan-in of the gate? Will it make any difference on the ability to compute?
Let me not go in there. I don't. This is a topic of circuits, and it's a whole class of classical computation complexity. Okay, so now we have P defined both by circuits and by Turing machine. And there are two equivalent classes. They are the same class, P, polynomial time. And in fact, we can think of other models of computation. And there are various models of computation that people have considered. Here is the beautiful Game of Life by Conway with its local updates of the state of this lattice, of this grid. And you probably know this. And each one of these models, like DNA computation, and here there's a billiard ball-based computation. So all these models basically are based on the same idea of you have local rules which are very simple, and by accumulating these local rules, you get the complexity. And it turns out that all these models are equivalent in the sense that they somehow, if you consider the class polynomial time, it's the same in all these models. And this is, so if you consider the class computations that takes quadratic time, then it might depend on the model. But if you consider it in the right resolution, polynomial time, then all the models are the same. So the overhead of moving from one model to another and simulating one by another is polynomial. And this is very important because it gives us robustness when we ask when is a function easy to compute, meaning in P, then we don't care which model we use. Okay, so, and this is captured by the very important thesis that's called sometimes referred to as the extended Church-Turing thesis, which says all physically realizable computational models, so any model that is sort of reasonable, that does not include things like, okay, I get the answer to the function in one step without working. So any model that is reasonable, like finite precision and finite energy and stuff like that, cannot do much better than a Turing machine, meaning a Turing machine can simulate it in polynomial time with polynomial overhead. Okay? Great. So there's one thing that we need to add to this extended Church-Turing thesis, and this is, in fact, if we add randomness, and that was realized, I think, in the 70s by Robin and Miller and others, if we add randomness, we could actually gain in computational power, or maybe we could. So what does it mean to add randomness? So I want to allow also the Turing machine to use random bits when it makes its decisions. Okay? And I can also do that with circuits. I want to allow the circuit to have access to uniformly random bits except for its input. And then the answer or the function that this circuit computes will depend, of course, on these random bits. So the function that it computes will be defined as if with probability at least 1 minus epsilon over the random bits, the answer here is 1, we'll say that x is in the language. And if with probability at most epsilon, the answer is 1, we'll say that x is not in the language. Okay, so this randomized circuit will compute the function f if it gives the right answer with all but epsilon probability. Then we'll say that it has error epsilon. Okay, so then we now can define the randomized class, BPP, with error epsilon. And we say that that's bounded probabilistic polynomial time. The bounded comes from the fact, we'll see that in a second. But bounded probabilistic polynomial time with error epsilon is the set of languages, L and BPP epsilon, if there exist polynomially growing in size circuits like that with access to random bits, such that for all n, for all x of n bits, if x is in the language, then with probability at least 1 minus epsilon, the answer is 1. And if x is not in the language, then with probability at most epsilon, the answer is 1, or with probability at least 1 minus epsilon, the answer is 0. Okay? And again, we have this uniformity condition, which we'll ignore. Okay, so question about this? This is the classical model. Let me just mention that the epsilon here doesn't really matter in the sense that we usually think of epsilon as a third. That's we make an error with a probability a third, but in fact this third is arbitrary. You can move it between different values of epsilon, and the reason is that we can use amplification or error reduction. What does it mean? So if I have epsilon which is bounded away from a half, that's the reason for the b here, bounded away meaning it's at most half minus 1 over poly n, then we can actually repeat this computation many times, and epsilon can be made exponentially small by repeating it polynomially many times and taking the majority. Okay? So if we take the majority, one can pretty easily show that by the Chernoff bound, if epsilon is less than that, the right answer is given with at least half minus 1 over poly probability. And that means that the expectation of the number of right answers is half plus 1 over poly. And by Chernoff, the probability that the majority will be less than a half can be bounded from above by exponential. So if you're not familiar with the Chernoff bound, check it out. It's something that allows us to sort of degrade the error exponentially. Okay, so questions about that?
Those conditions need to hold for larger or for
Which condition?
the probability. The condition that the probability of error is bounded from below.
This thing? Or are you talking about this thing?
The inequalities, the bound, the inequality. Yeah, do they need to
I start here, here?
Yes.
This one. This needs to hold for any n. and for every x.
Okay.
Okay? So we require that for every x, the probability over the random bits is such that the answer is 1 with at least 1 minus epsilon probability. Okay?
It's not enough that it will hold for large n, or like in the limit of large n.
Well, if it holds for large n, then it holds starting from some finite n. And then, of course, it's enough because up to that finite n, it's a constant size circuit, so you can stick it into this polynomial. You can sort of find circuits that will just compute it up to this finite n on your own. It's finite. Okay? Okay, good. So now we're ready to move on to the quantum world. Before that, let's just summarize it in a computational complexity map. We have here P. We have BPP, the class of problems solvable in polynomial time by randomized computers. And just to put things in context, we don't know whether BPP is different than P. Okay. For example, here is perhaps the most important example: the problem of polynomial identity testing. We're given a polynomial in some succinct description. It's a polynomial over n variables, and say you're given it by a circuit that computes it, evaluates it for some inputs. But think of this polynomial as if it's over n variables. It's given to you as, say, a product of brackets, 1 plus x times 1 plus y squared times 3x minus z to the 4, etc. Opening it up, you can get exponentially many coefficients. So just, if we want to answer the question, is this polynomial identically 0, we will need to actually open up all these brackets, and it will take exponentially long. There is a randomized algorithm that does it, and roughly what it does is just take a large field and pick random values to the variables, and then evaluating the value of the polynomial at these values is easy. You don't need to open up the brackets. You just evaluate the value of the brackets. So then that's easy, but it's random because you've picked random points in the field. So we don't know whether polynomial identity testing is in P, but it is in BPP. But we strongly suspect that BPP is equal to P. There are good reasons for that, which we won't get into here. Okay, so given that we don't yet know whether BPP is equal to P, we are going to update the Church-Turing thesis so that actually we're talking about, we will say that randomized Turing machine, rather just Turing machine, is what captures the class of tractable problems in our world up to quantum. The extended randomized Turing machine will say all physically realizable computational models can be simulated in polynomial time by a randomized Turing machine. And before quantum computation arrived, this was basically the belief that randomized computation defines polynomial time, defines what can be done. Okay, I should mention that NP here is another class that will be mentioned later in the school, and well, okay, I won't define it, but we'll see it. But this is its relation to BPP. We don't know its relation. Okay, so there was a question, but with a mic.
I just wondering why the BPP is not contained in NP.
Why the BPP is not contained in NP? Because of the randomness. We don't know how to handle the no case. BPP is allowed to make error also in both directions.
But the non-determinism won't help for randomness?
It helps only if the error in the BPP is one-sided, which is called RP. And then it's true that NP contains RP. But NP is much, much stronger because NP talks about the existence of one string out of all these random strings that leads me to the right answer. Okay, so Okay, so now how do we take this model and make it into a quantum model? So let's go through what Orr described, but slightly more formally. So we start with a quantum bit, a qubit. And the special thing about a qubit is that it can be in a superposition of 0 and 1 for us, and actually, שעה וחצי. No, שעה וחצי. So we start with, okay, wrong day. Okay, so we start with, where was I? What was the sentence I was just saying? It was important.
Superposition of past states.
No, okay, never mind. I'll get to this later. I'm sorry? Yeah, okay. So, so anyway, we have a qubit which can be in a state 0 and 1, and in a superposition of all its possible states, meaning a linear combination of 0 and 1. The important thing was that Orr said we cannot abstract the physics out of it. I want to say the opposite. We can abstract the physics out of it after we've taken a 1-hour course on quantum computation. The whole idea of quantum computation is in fact, I think the whole strength of this field is that it looks at physics, and with all its really a huge variety of systems, etc., and it abstracts the mathematics of quantum mechanics. It's true that this mathematics is different than that of classical mechanics, but it abstracts this mathematics, and once it does so, we can forget about the physics. And that's a big relief, at least for mathematicians, that we don't really have to understand electrons and fields, etc. We can talk about the mathematical models, okay? But we still have to make the effort of the 1-hour sort of building up of the model. Okay, so so the qubit that we are going to use is described by a state in the Hilbert space, in a 2-dimensional Hilbert space, spanned by 2 states, or 2 orthonormal states, the orthonormal basis, 0 and 1. And as Orr described, it's just the Ket notation, the Dirac notation, for 2 orthogonal unit vectors. With this restriction that a squared plus b squared, the absolute value, is 1. Now, a measurement is a very weird process that Orr again described, and I want to just emphasize one thing. This measurement has 2 outcomes, 2 results. One is a classical result, which is sort of what's written on the measurement device at the end of the measurement. And the other is what happens to the quantum state. Of course, these are correlated. And the whole thing is probabilistic. Quantum mechanics doesn't give us a recipe of how the measurement acts. It just gives us the statistics of how it acts. And this is inherent and very disturbing conceptually and philosophically, but we'll take it for granted. So, so the point is that if you have a state like that, and if you measure it in the basis, in the standard basis, which we'll often call the computational basis, that means that we ask the system if it's in 0 or 1, then it answers, yes, I'm in 0, with probability a squared, and then it collapses to the projection of this state on 0. Actually, there is an a here, and the state is renormalized so that the new state is also of norm 1, so that the interpretation of probabilities to these coefficients is retained. Okay, and then with probability b squared, we get 1. And again, the state is renormalized. So the system, both the quantum state collapses, and there's a classical answer. The result of this collapse was 1. Okay? Okay, let's say it slightly more formally. And for that, we have to define the inner product that we're going to use. So if these are the 2 states, then an inner product denoted by psi and phi. Psi is just the line vector. If you want to think, I think one of the most difficult steps in starting to think in quantum computation language is to move between the vector language and the Dirac notation. And the other step is, will come in a moment. But so if you want to think in vector notation, then psi, like that, will be A0 star and B and A1 star. That's the lying vector. And phi is the standing vector, and then the coefficients come without any star on them. And then the inner product is just the usual inner product, like matrix multiplication. Okay. And then, so now suppose we want to apply a measurement on this. Well, we need to say what do we want to measure? And by this, the way physics describes it, or the way we are going to describe it, is by what's called an observable, that is a Hermitian operator. For example, this Z, that's a Hermitian operator. And the point is that this Hermitian operator can be diagonalized, and it has eigenvalues and eigenspaces. And so the measurement, basically what it does is it takes the state and projects on an eigenspace with probability, which is the norm squared of the projection of this state on that eigenspace. And the result will be, the classical result will be the eigenvalue. Okay? So let's see if I have an example here. If I write down psi as in terms of the basis of eigenvectors of this Z matrix, then the probability for 0 is just the norm squared of the projection of psi on the space 0, spanned by 0, which is A0 squared. And likewise for 1. Is that clear? I think this is the last time we're going to actually define measurements. So, okay. We can also measure in a different basis. Think of the basis that takes the eigenbasis of Z and maps it by a Hadamard to a different basis. Hadamard is unitary, it preserves the angles. So also the new basis is an orthonormal basis. And this new basis is plus and minus. And this one can check is exactly the eigenbasis of X. X also has eigenvalues plus and minus 1 with these eigenvectors associated with them. And then the probability of measuring, if we measure with respect to this basis, this state, the probability for plus is going to be, again, the norm squared of the projection, which is just the inner product psi with plus squared. And you can check that it's just this value, and for minus, it's just this value. Okay? And now more generally, we're not just going to talk about qubits. We can talk about qudits, systems of more than 2 dimensions, say d dimensions. And then we can talk about measurements, observables, of d by d, a d by d matrix. And this matrix will be written as a sum, can be decomposed into a sum of projections on these on its eigenspaces, pi j, with eigenvalue lambda j. Okay? So the observable M can be written as a sum over j, lambda j, pi j, where these pi's are projections on eigenspaces. And in that more general situation, the probability that we take a state psi and project it onto the eigenspace pi j, the probability that we get the outcome j, is again the norm squared of this projection, pi j psi squared. Okay? Now, I want to just say out loud a confusion that is often maybe confusing people that are not used to it. We often confuse between classical outcomes being the eigenvalues and classical outcomes being the name of the space. So for example, in Z, when we measure, the classical outcome could be, I have been projected to 0, to the state 0, but the eigenvalue associated with 0 is what? 1. So actually I could get the eigenvalue 1, of course with the same probability. And this question of which one we're using is something that you'll have to understand from context. Okay, whether we're using the eigenvalues or the actual way to say this is the eigenspace. Yeah, not much. I'm just trying to give you some help in navigating the literature as well. Yeah.
Does it matter what values do you take to be the lambda j's? I mean,
Yeah, it matters. So, okay. The question was, does it matter if I change lambda j's? It doesn't matter to the statistics at all. And of course, it doesn't matter to what happens to the state. But sometimes we will actually be interested in the values of these eigenvalues. So for example, in Sandy's talk, we'll talk about observables which are energy operators called Hamiltonians. And then these lambdas are the energies. So they have physical meaning, and we'll be interested in the meaning of these eigenvalues. And then it will be very important that we actually talk about the outcomes, the classical outcomes being the eigenvalues. Okay, good. So question before we move to n quantum bits. Yes.
I just wondering what's the difference when we pick a Hermitian matrix or just a basis for a measurement?
Well, the difference between picking a basis and the Hermitian is that the Hermitian matrix actually tells us which subset of these basis states have the same answer. So if, for example, we'll see an example for that in a moment, okay? Yes, no, never mind? Okay. Okay, so n quantum bits. If we have n quantum bits, we start with, we need to somehow say how we combine these qubits or qudits into a single system, if we have n such systems. And the way we combine it is by the tensor product that Orr described. And I'll say it again, because this is sort of the basis. We need to understand it very well. Okay, so basically, if we put n such qubits together, they're described by the tensor product of n Hilbert spaces or vector spaces that each one corresponds to a single qubit. So what does this space mean? Well, the space is essentially simply the space spanned by the following 2 to the n states. So we take for each copy, for each qubit, we take a basis 0 and 1, an orthonormal basis. And we have 2 such vectors for each one of the copies of the qubits. And what we do to build the tensor product space is we take the tensor product of all possible configurations. So we take 0, tensor, 0, tensor, up to 0, n times. That's the first configuration. Or 0, tensor, blah, 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 1, tensor, 0, tensor 1. That's the second configuration, etc. Up to 1, tensor, blah, 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 tensor 1, tensor 1. So the number of such choices is 2 to the n. And the number of coordinates here is n. Okay? So the dimension of my space, which is spanned by these basis vectors, is 2 to the n. And that's the mind-boggling thing about quantum systems, that the dimension that they live in is exponential. And so a general state, psi, is a superposition or just simply a linear combination. Superposition is just a linear combination jargon. A linear combination of all these 2 to the n possible strings. And we'll often omit the tensor product and just refer to this state as the same as this state. Okay? And even more than that, we'll often omit these bits, and we'll just take this as a binary representation of some number. So we'll just put here a number, an integer between 0 and 2 to the n minus 1. Okay? So now the point in this definition of of this space is that it's kind of very hard to grasp. How can a physical system, a classical physical system of n bits is described by n bits? A quantum system of n qubits is described by 2 to the n complex numbers, or real numbers if you want. How does nature actually update all this information in it? I don't have an answer to that, but think of 500 qubits. In general, the state that describes the system requires 2 to the 500 complex numbers to describe, which is more than the number of particles estimated to be in the universe. So it's a very small system, 500 qubits, but its state in general requires 2 to the 500 complex numbers to describe. Okay, yeah.
Can you maybe contrast this with just plain old probability distributions?
Yeah.
Also?
So of course, if you have a probability distribution, you also in general require exponentially many real numbers to describe it. But in fact, the state of the system is just one of them, and we just don't know it. Here, as far as we know, the only way we can describe the state of the system is somehow by carrying with us all the superposition. We can't just focus on one of them and say, we don't know where we are, but we are in one of them. No, we need to somehow carry with us the entire superposition, because somehow these coefficients are going to talk to each other, as we'll see in a little bit. Okay? So, okay, and this distinction between linear and exponential was already mentioned as very surprising by Orr in the early 80s. Mani and Benoist and Feynman noticed this exponential explosion in the number of in the size of the description, and said maybe we can use that. Maybe the computation, maybe somehow the fact that the system is so hard to simulate means that it encompasses in it some very strong computational power. So maybe you can actually use it as a computer. Okay, so now, yeah.
What happens if you take like all states of n bits and then remove all entangled states? So what is the space will be?
All states of n bits, and we remove all entangled states, we'll just get all tensor product states. And this is a very easy space. It's not a space, actually, because it's not a linear space. If you take superpositions of non-entangled states, you get an entangled state. But the set is a very simple set. It's just tensor product states. And then each of these states can be described by just describing each of the single qubits. So 2n numbers. Thank you.
So quantum powerful comes from entanglement.
Yes, so quantum power comes from entanglement. This is the next thing that I wanted to say, that if we look at these states and we look at the superposition of these 2 to the n basis states, most of the information lies in the entanglement between the different particles. If you just refer to states which are not entangled, which are tensor product states, you can describe them by a linear size description. Okay, and so understanding the nature of multipartite entanglement is this is the whole field. It's trying to actually give us some handle to understand what's going on with such states. Okay, so I should just say there is another way to describe quantum states. I'm not going to explain it very, very well. I'm just going to mention it. In the problem session, in the TA session, Chinmay is going to describe a little bit about reduced density matrices and matrices in general. But let me just mention it so that it won't be completely new. This is a quantum state, or this is a quantum state. It's called a pure state. It's a vector. We can also assign to it a matrix. That's called the density matrix. And that's just the outer product of psi with itself. So the ket version with a bra version. And this is just, as we've seen here, this is a standing vector times a lying vector, complex conjugate, and so we get a matrix. And notice that we get the same matrix even if we multiply psi by what's called the global phase, e to the I theta. because when we multiply it by the complex conjugate of that, we get e to the I minus theta, and this cancels. So we could think maybe this rho, this density matrix, loses information. It lost the global phase. But in fact, that's the only thing it loses. And moreover, the global phase is not a physical thing. If you apply measurements on these states, as we'll see in a moment, you cannot measure the global phase. The measurements actually are not affected by the global phase. So this density matrix is in one-to-one correspondence with the physical system in a pure state. The advantage in using density matrices is that it actually enables us to describe in a concise way not just pure states, but also probability distribution over pure states. And this will be needed later on when we talk about subsystems, where when we have a subsystem of a larger system, like the EPR state that Orr described, 0, 0, plus 1, 1, we can ask what is the quantum state of the first qubit? And the quantum state of the first qubit is something that is not, it doesn't have a vector. There's no alpha tensor beta that is equal to 0, 0, plus 1, 1. And so the first qubit there's no alpha that describes it. But there is a matrix, there is a density matrix that describes it. And this density matrix corresponds to a probability distribution over states, over pure states. And so the density matrix for a probability distribution over pure states is just the convex combination of the density matrices for each of the states in the mixture. By the way, those who cannot see in the back, the slides are on the side. Can you see on the side? I see people sort of trying to see in the bottom, but it's supposed to be more helpful. Okay, so good. So now let's see how we act with quantum gates on these states. And the first thing is I don't think Orr mentioned Schrödinger's equation, right? Where's Orr? No, he didn't mention Schrödinger's equation. But the evolution or the dynamics of such quantum states are governed by what's called Schrödinger's equation, written here, with the energy Hamiltonian that I mentioned, the energy operator that I mentioned before, here, acting on psi. We're probably not going to delve too much into the Schrödinger's equation, but all I wanted to say is that when this is a differential equation. When you integrate it, you get that when you integrate it from time 0 to time t, you get that psi has evolved by a unitary operator to u of psi. Okay? And, well, okay. And the unitary is u times u dagger, transpose complex conjugate, is identity. So this is a rigid rotation of the Hilbert space. It preserves the angles and the norms. Good. So, okay, so let's see how we act with a single simple quantum gate on such an n-qubit state. So let's consider the NOT state, the NOT gate here that takes 0 to 1, 1 to 0. Well, and we can also ask what about the Hadamard gate and what about the CNOT gate? Wait, do I have here the... yeah, so these are quantum gates that we have seen before, the NOT gate and the Hadamard gate. CNOT we haven't seen before. It's a very, very important gate, so let me just spend 1 second on it. It's a 2-qubit gate, and what it does is, here it's written in a concise way of how it performs, how it acts on basis states. Of course, it's linear, so it acts similarly by linearity on any superposition. So if A and B are both just bits, then what it does is AB goes to A XOR B, so A plus B modulo 2. So if A is 0, then what happens here is that B is XORed with 0, it just remains B. But if A is 1, what happens to the right coordinate is that B is XORed with 1, so B goes to not B. So if A is 0, nothing happens to B. If A is 1, then B is flipped. That's why it's called the controlled knot. It seems not to do anything to A, just to B. Okay. Notice that if B is 0, then A0 goes to AA. It just copies the bit A to the side. Okay, so these are interesting quantum gates. How do they act on a state? So the thing is, everything is linear. All we need to understand is how they act on a basis state, on a string. So how do they act on a basis state? Well, suppose we want to apply the NOT on the leftmost qubit on this string. Then 0 will be flipped to 1, but everything else will stay the same. Just the simplest thing that you can think. Likewise for Hadamard. Hadamard will just act on this qubit, will map it to 0 plus 1, and everything else will stay the same. By linearity, we can extend it to a superposition, and then, again, by linearity, we'll have a superposition of this x acting on this string for all the strings. So I want to mention one thing that this is, again, very confusing, the notion of locality. These are local gates. If I look at the Hilbert space, locality could mean that I am looking at a single dimension out of the 2 to the n dimensions. But in fact, locality in the physical space of n qubits means something completely different. I can act locally on a single qubit, and what it does, say I act locally on this qubit and I flip it. What it does, if I'm in a superposition of 2 to the n strings, is that it affects all the strings, all the basis states, meaning all the dimensions simultaneously. Okay, so it has a highly non-local effect in the Hilbert space. Okay. And formally this is written as the tensor product. This is just the tensor product of x with identity on the rest of the qubits. In density matrix language, what this does is psi will go to u psi times the dagger of u psi, which is this. So it just conjugates the density matrix. But we won't be using this later. Okay, so that's it for quantum gates. Yeah.
Hi. You mentioned that the unitary evolution of quantum states is like similar to the quantum gate. But the unitary evolution has eigenvalue, which is energy. Those eigenvalue means
the unitary evolution doesn't have eigenvalues, which are energies.
No, e to the minus Hamiltonian.
It's e to the I, the energy. Yeah.
So I'm talking about e to the minus Hamiltonian.
Right.
Then this energy of these operators has meanings in physics. Does it has also meaning in circuit complexity?
The energy of which operators?
So let's take like CNOT gate or Hadamard gate. Then we can construct Hamiltonian of the gate, right?
Yeah.
And it will have eigenvalue because it can be represented with the matrix form. But if it is a physics, then that eigenvalue is an energy of the system. But what does those eigenvalue of the gate mean?
Well, I don't think let's talk about it offline, because it's not, I have something to say about it, but it will digress us to other places, okay? Okay, so what's a local measurement? I mean, how do I apply measurements on such n-qubit states? Okay, so here is a state, and we want to apply a measurement. And like I said before, we can measure with respect to any Hermitian observable by decomposing this observable to its eigenspaces and eigenvalues and projecting onto one of them, and that's the probability to project. But what does it mean to measure a local observable? I mean, this would not be a local observable. This would be just a matrix on the n-qubit Hilbert space, 2 to the n by 2 to the n matrix. What does it mean to measure a local observable? For example, how do I measure the first qubit in the basis of z, in the eigenbasis of z? Well, the idea is simply to look at this observable as a tensor product with identity with the rest. So the eigenspaces of this observable, when viewed as an observable acting on n qubits, is just, there are two of them. The first eigenspace is spanned by all states starting with 0. So 0, 0, 0, 0, 0, blah, 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 all the 2 to the n minus 1 first strings. That would be the first eigenspace. And the eigenspace, the second one, will be everything that starts with 1. Okay? So when we say we measure the first qubit, we basically mean that we look at the decomposition, the direct sum of these two subspaces, and we ask whether the state can be projected. What's the projection, the norm of the projection of the state on the first subspace? What is it on the second subspace? So this is, we start with a state, and we write it as the superposition of 0 tensor something plus 1 tensor something, and then the probability to be projected on this state, which is the projection of psi on the first subspace, is just A0 squared. And after this projection, the state will be projected to that eigenspace. Okay, so that's what it means to measure a single qubit. Is that clear? Yeah? That's what it means to measure a single qubit in the computational basis. And in the same way, I could have talked about measuring that qubit in the X basis or in any basis, and then the subspace would just be spanned by the eigenstate of that, say, single qubit, tensor with everything else. Okay? Yeah. I'm going to stop the questions in a bit too, so that I can actually reach what I need to do.
Okay, just a quick question. If we change coordinate for the measurement, will it...
If I change what?
If I change the coordinate of the measurement...
Like from 1 to 2? If I change the qubit?
Like from computational basis to Fourier basis, will it change the local property for the measurement?
No. So I can talk about a local measurement in the Fourier basis, like the Hadamard, the X basis, for example, the plus-minus basis, for a particular qubit, and it will still be a local measurement, because the space, the two spaces will be, the first one will be plus tensor everything else, all other states on the last n-1 qubits, and minus tensor that.
But the change of basis need not to be like Hadamard or composed of local operator.
Yeah. So of course you can talk about change of basis where you which is not local, and then the resulting measurement will not be local. Okay. Once again, this is something that will go into the problem set, and we'll of course practice that. You can't really understand this without doing something with your hands on. Okay. So in density matrix formalism, this becomes much easier. Probability for projecting on the jth eigenspace is going to be written as the trace of the density matrix times this projection. I'm not going to prove that. I'll defer that to later. Okay. An important example, a very important example, that will demonstrate interference and the importance of CNOT and what's called the principle of delayed measurements. Okay, so remember the coin flip that Or talked about last talk. You can think of Hadamard as some kind of a quantum coin flip, very roughly. So 0 goes to 0 plus 1, and then if we measure this bit, we get a random bit. Now what do we, if we toss a random bit twice? Of course, if we toss a random bit twice, we get still a random bit. If we take a coin, flip it, and then we flip it again, we get a random bit. But if we apply Hadamard twice, we no longer get a random bit, we get a deterministic bit. That's easy to calculate. Simply, you can just check that h squared is the identity, but you can also check it differently by applying h on 0 and then applying h again. So h on 0 gives you 0 plus 1 over square root of 2. And applying h again, by linearity, 0 goes to 0 plus 1, 1 goes to 0 minus 1, and 1 and minus 1 cancel. And therefore we get deterministic 0. Okay? And this is what we call destructive interference. The cancellation of the weights, which could be positive and negative on the same thing, coming from, so 0 contributed to 1 weight a half, but 1 contributed minus half, and they canceled. And this simple phenomena is so important that it deserves another picture to look at, okay? So let's look at it. Using what's called Feynman path integral, which is a very fancy name in this case for basically a picture for matrix multiplication. So what does this mean? What I've written here is sort of all possible states, 0 and 1, before the Hadamard, and then after the Hadamard, after the first Hadamard, so before reaching this state, that's the second Hadamard. And on the arrow, I've written the matrix coefficient, the matrix term that connects between 0 and 0. So it's 1 over square root of 2. Okay? And here, too, we have 0 going to 1 with amplitude 1 over square root of 2, with coefficient 1 over square root of 2. And therefore, 0 goes to 0 over square root of 2 plus 1 over square root of 2, 1. Okay? That's the first Hadamard. Now we do exactly the same thing. And again, 0 goes to 0 and 1 with weights 1 over square root of 2 and 1 over square root of 2 on each one of the arrows. 1, on the other hand, goes to 0 and 1. 1 to 0 contributes, what's the weight? Hadamard takes 1 to 0 with what coefficient? 1 to 0 with coefficient 1 over square root of 2. But 1 to 1 with coefficient 1 minus 1 over square root of 2. So this arrow gets a minus sign. Now what's the amplitude, what's the coefficient in front of 0 at the end of this 2 Hadamards? Well, just like matrix multiplication, it is matrix multiplication, you have to sort of run over all possible intermediate values and sum over all the possible path going through all intermediate values. So the contribution of the path that goes through 0 is the product of the weights on the arrows. So the path, this path contributes a half, whereas this path contributes a half. So they sum up, and the amplitude in front of 0 is 1. But on the other hand, if I look at 1, this path contributes a half, but this path contributes minus half, and they cancel. Okay? And this is destructive interference. The different paths cancel out. And so the fact that weights on arrows can be negative, this is a very important point in quantum algorithms in general, and in quantum phenomena in general. And we'll see that in Adam's talk later on when we talk about quantum algorithms. Well, actually, this is happening also when we talk about interference patterns over n qubits, not just a single qubit. And the sort of the magic in thinking about quantum algorithms over n qubits is that somehow we want to design those interference patterns in such a way that good answers will constructively interfere, and bad or things that we don't want to measure at the end will destructively interfere and will cancel each other. Okay? So this is, okay, we'll talk about this later. Okay, so now this was one example with talking about this diagrams, the Feynman path integrals. It's going to be very interesting to see what happens when instead of doing this, we add a small modification. So instead of doing Hadamard and then Hadamard, we measure in the middle. What do you think will happen? If we didn't do that, we got a deterministic 0. If we do measure in the middle, what do you think will happen at the end? Huh? What I'm asking, if I take a qubit in state 0, apply Hadamard, measure in the computational basis, and then Hadamard again, and measure. What do you think the result will be? Huh? Same as the first? No. No, so this calculation breaks down because after this measurement, 0 and 1 are no longer in superposition. We have probability half to be here and probability half to be here. So we're either in this situation or in this situation. They cannot cancel each other. So it doesn't look the same, and it's not the same. let's see what actually happens. If you apply the Hadamard, you get 0 plus 1 in a superposition. Then you measure. You get either 0 or 1 with probability of half. So you're either here or here. Now you apply the Hadamard again. If you have 0, if you ended up in 0 in the first measurement, then you get a superposition of 0 plus 1. And you measure, what do you get? One of them with probability half. And if you ended up with 1, you apply the Hadamard, you get 0 plus 1. You measure, what do you get? Same, half, half. So the measurement in the middle ruined the interference pattern. Okay? Good. So now I have a question. Can we do this unitarily? Can we, instead of measuring, can we ruin the interference pattern by applying some unitary operator? And it turns out that the answer is surprisingly yes. So let's look at the following parallel example. Instead of the measurement, we're going to apply a CNOT. To remind you, a CNOT is AB goes to A XOR B. But we're going to apply it on an additional qubit, so the first qubit plus an additional qubit, initiated to 0. The additional qubit is going to be initiated to 0. So remember, when B is 0, A is just copied to the other side. So that seems like it's not going to matter. We just copy the bit on the side. How can it affect anything? Okay, so the thing is that it does affect. So let's see. Let's see again, using Feynman path integrals, how can we see that it does affect? So, okay, maybe before I say that, I'll just say, I chose the colors here importantly different. Importantly, I chose the colors different between the two. This is yellow and this is red. And the reason is that they sort of live in different worlds. We're either here or here because we measured. So the key point is that also the CNOT effect will have the same implication, that they're sort of in different worlds and they cannot talk to each other. How do you see that? Well, let's look at the 4 states of these 2 qubits, 0, 0, 0, 1, 1, 0, and 1, 1. The first Hadamard on the left qubit takes us to 0, 0 plus 1, 0 with amplitudes 1 over square root of 2 and 1 over square root of 2. So we are in this plus this. Now, what does the CNOT do? CNOT on 0, 0 does what? Gives what? 0, 0. So we get 0, 0. And CNOT on 1, 0 gives 1, 1. So we get 1, 1. Now we are in a superposition of 0, 0 plus 1, 1. And now we again apply the Hadamard on the first qubit, 0. 0, 0 goes to 0, 0 plus 1, 0. 1, 1 goes to 0, 1 minus 1, 1. All with coefficients 1 over square root of 2, but which I ignore. I care about the sign. But the point is that now no longer is it true that the red and yellow arrows coincide. It's as if the fact that we wrote 1 on the side here versus 0 on the side here makes them in different worlds. They act in different worlds and they can no longer destructively interfere. And therefore one can actually show, and we will show that in the problem set, that the effect of this thing and a measurement is exactly the same. The way to show it is using reduced density matrices formalism, which will actually just look at the first qubit, the leftmost qubit, and say the density matrix, the state, the mixture, the mixture over random pure states describing the first qubit is the same for in this case as in this case. And we'll have to argue why the fact that the density matrix is the same means that they're actually equivalent physically.
What is the significance of this equivalence?
What is the significance of this equivalence? We'll see in a moment. I repeated the question. Okay. So this is called the principle of delayed measurement. Okay? And we'll see that if we get to it soon. Okay, so that's the principle of delayed measurement. Quantum circuits. Ta-dam. We were supposed to be there 20 minutes ago. What's a quantum circuit and what's the class BQP? That's bounded quantum polynomial time. So a quantum circuit is just a sequence of such gates acting on an input state. So we start with 0, 0. We start with some computational basis state. We apply unitary gates. And then at the end, we measure some qubits which are designated as the output qubits. Okay? Here are possible gates that we can apply. And the complexity, meaning the size of the circuit, is the number of gates. Okay? Good. Which gates are we allowed to use? So this is a whole subject that's called universal set of gates, which I want to just give you the beginning of, the most important part. What is it that we want from our set of gates? Like, which gates would you choose? Not Hadamard, is this enough to design quantum computations? Like, if I only choose single qubit gates, would you, if I have a lab that can implement only single qubit gates, and I'm telling you I can do any single qubit gates I want on n qubits, is this a quantum computer? No, why? There's no entanglement. The state is always a tensor product. So the question is, what constitutes a quantum computer? And this is given by the definition of universal sets of gates. What is basically, without reading the full definition, basically I want a set of gates that allows me to approximate any unitary on any number of qubits. Formally, G, a set of unitary gates on SU, special unitary group, determinant equals 1. That's just, you can ignore this S. On K qubits is universal if for all n larger than K, the subgroup in the unitary group acting on n qubits is generated by these gates, the subgroup generated by these gates, when I am allowing to act with each gate on any subset of K qubits. Okay? So when I have a gate, I can act on it on any choice of the qubits inside these n qubits. So when I multiply such gates, I get a dense subgroup in the unitary group on n qubits. Yes? Hadamard is not the dominant one? Yeah, so just multiply it by a phase so that it is. You can ignore this issue of determinant 1. It's not important. Yes? I'll just repeat the question so we don't bother about the mic. In what metric do you mean? Yeah, so just the operator norm. Oh, I promised to repeat the question. When I say dense, in what topology do I mean? In what metric? The operator norm. Now you need to repeat the question.
Because the elements of this SU2K, they come from like smaller space, so you need to take the tensor with the identity.
Yes. Oh, yeah. Thank you. So do the question. Yeah. Do the unitaries when they come from a smaller space, you need to somehow give meaning to what I mean by applying them on n qubits. I just take tensor product with identity on the rest. Okay. Thank you. So that's universal sets of gates, and here are some examples. I won't take now further questions because I need to somehow get to the thing I have to get to at the end. So universal sets. Here are some examples. First of all one qubit gates plus the CNOT. That's universal. You can approximate any unitary on any number of qubits using this. Here's another set. Hadamard plus just 2 gates. Hadamard and what's called the controlled P. P is this 2 by 2 matrix, meaning a single qubit, and controlled P meaning you apply P on the second qubit if the first qubit is 1, and if it's 0, you don't do anything, just like controlled NOT, but controlled P. So these 2 gates are also universal. And the Clifford group and the T gate, this is the T gate, is also universal. I want to find the Clifford group. It's some a nice group within the unitary group, which surprisingly is possible to simulate classically, and it's we will hear about it many times in this course. But anyway, I just wanted to say there are various universal sets of gates, and great, so that we could use maybe any set of gates that we can somehow implement in the lab. Are they different? So before I answer this question, are they different? Do they give different quantum computers? I want to refer first to this notion of dense. Here I only approximate a unitary. Why does it what do I lose by that? I have to somehow argue that the result, the outcome, meaning the probability distribution over the measurement at the end, is very close if I manage to approximate u to within a very small epsilon. So that's true. I want to walk you through the argument, but it's very easy. It just uses the different norms, several different norms that are appropriate. So if u minus u prime is at most epsilon in the operator norm, then acting on a state on the same state, the resulting two states will be very close in the Euclidean norm, and then in the appropriate metric on density matrices, which is the trace norm, that's the sum of the absolute value of the eigenvalues, if you want to know that, then the two density matrices at the end will also be very close. And it's possible to show that if you have managed to approximate the final density matrix to within a very small epsilon in the trace distance, then any measurement that you apply will have very similar distributions on the two density matrices. So the right metric to use for two distributions is the total variation distance. That's the L1 distance on distributions. And so any measurement on a state gives you some distribution. And if you have two very close density matrices, their distributions with respect to that you get from measuring the same observable, these two distributions will be very close also. So you need to walk through this argument slower, but this is true. So approximation is good enough. It is good, but it's not clear that it's good enough because it depends on how fast you approximate each gate. It could be that you can approximate a gate, but it takes you very long to get to very small epsilons. So now comes a magical theorem called Solovey-Kitaev theorem that basically says, no, don't worry, everything is under control. Density implies efficient density. So if you have universality, you actually can approximate any gate very fast. Okay, so let me say that more precisely. Let me state the theorem. Okay, what does it say? G, a set of gates in the unitary group acting on k qubits is universal, then for all n larger than k, for a given epsilon, and a given u on n qubits, there exists a sequence of gates from this set, again, tensor product with identity. So you choose which qubits it acts on, such that the product of these gates minus u is at most epsilon. And the important thing is that L, the length of this product, the number of elements, grows only polylogarithmically in 1 over epsilon. Okay? So that's great. You only need polylogarithmically in 1 over epsilon gates in order to approximate the unitary that you want. Clearly this is too good to be true, right?
Exponentially with that.
Right. So the thing to notice, the catch here, I should say that this is basically a glimpse of a whole field of how fast can unitary gates approximate unitaries. It is related to expansion in the unitary group, and there are lots of results starting from Sarnak and Bourgain and Gambord and Ori Poljanszewski from here and others. And you're welcome to look at this reference if you're interested in that. This sort of talks about the efficiency, this constant here. But we only care about C being a constant for now. This looks too good to be true, right? I mean, it seems as if you can approximate any matrix to epsilon logarithmically in 1 over epsilon. Of course, this is not, there's something hidden here. And the hidden thing here is that, notice the catch, this is true for any fixed n. But if you vary n, we have to look at how the constants in this O depend on n. And these constants depend very strongly on n. This O, the constant in O, will grow exponentially with n. Okay? So that we can relax. We cannot approximate any unitary so fast. And this makes sense because just the counting argument tells us that this is impossible for n being very large. as long as n is constant, then you can move between a unitary and gates from a universal set that approximate it very easily without too much overhead. But if n is large, this is impossible. And the counting argument is simply that, well, I want to say that if I have an n-qubit matrix, there are n-qubit unitary matrices that will require exponentially many gates to reach to within even a constant epsilon, say a half. And the counting argument is simply look at the number of radius epsilon balls in those unitaries, and you'll see that their number is doubly exponential in n. And therefore, if you just count the number of possible sequences of gates of length which is less than exponential, there's just not enough of those. Okay, so good. But as long as we restrict ourselves to constant number of qubits, then we can move using universal sets of gates between different. We can approximate any gate that we want, as well as we want. Okay, so now we can say something about the independence of this whole definition that we said on G, the universal set. And this goes as follows. So this is switching between two sets does not cost too much. So the theorem is basically just what I told you before. Let me state it. Just what I told you in the last minute. Let me restate it. Let G and G prime be two universal set of gates on k qubits. And given epsilon and a quantum circuit over the first set, G, with m gates acting on n qubits, which applies the unitary U. So I have a circuit applying U using one set of gates. I want to translate it into a circuit that uses a different universal set of gates. Well, the theorem says that you can do it. Then there exists another quantum circuit which applies U prime. U prime minus U is at most epsilon, using only O of m polylog m over epsilon gates from G prime. So the overhead is just polylogarithmic. And the proof is very easy. By Solovey-Kitaev, given Solovey-Kitaev, it's very easy. Approximate any unitary gate from G in this circuit up to epsilon over m, and that requires only polylogarithmically many gates. So what we have is a sequence Okay, so what we have here is a sequence of G, L. That's the desired sequence of gates. And each one is approximated by some Gi prime. And Gi minus Gi prime in operator norm is at most epsilon over m. Okay, so I want to estimate this, the operator norm of the whole thing. And it's easy to understand how this works, remembering that G's are unitaries. So we can write this as a telescopic sum of GL G1 minus GL prime GL minus 1 up to G1 plus GL prime GL minus 1 G1 minus GL prime GL minus 1 prime. So you get what I'm doing, right? Each time I'm replacing one of the non-prime with a prime. And up to G prime L up to G2 prime G1 minus GL prime blah 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 G2 prime G1 prime. And so this is equal to that, but using the triangular inequality, this is at most the sum over these differences. And notice that each one of these differences, and the difference between this sequence and this sequence, is just in a single unitary. And so for a single unitary, I know that Gi minus Gi prime is at most epsilon over m. So how do I know that this thing, for example, is at most epsilon over m?
The
Yeah, exactly. So the distance is invariant under unitary transformation. So I can write this as GL minus GL prime times the unitary. And so that the first unitary will not affect anything. So error is additive. That's the point of this argument. And therefore, it's enough to approximate any one of the gates sufficiently well. Okay, so that's good. So everything we're doing is independent of which universal sets of gates we're using. And that gives us robustness. We don't really need to insist on one universal set of gates. That's like switching between different programming languages. We can use one that we want. If it's comfortable for us to use one universal set of gates for writing algorithms and another to implement in the lab, then we can switch between them.
What you said, that all this is relevant when n is fixed, and what do you do when n is
Yeah, so it is, I was using it only when n is fixed because I'm starting with m local gates, and then I'm replacing each one of these local gates by a sequence of local gates from the other set. So I'm fixing these universal sets of gates contain gates on a fixed number of qubits, a constant number of qubits. And then the circuit will act on n qubits, but each one of the gates are, okay? Thank you. Okay, good. So BQP. How long do I have?
9 minutes. Plus mine.
Okay. So we'll have to run a little bit over the last few slides. Or maybe take 5 more minutes. Okay. So BQP is the following thing. So now we have arrived to what we have worked so hard to do. We can define the class of polynomial time quantum computations that can be done by polynomial sized quantum circuits. Okay, that's BQP. Here's a quantum circuit. These are the quantum gates. Here is my input x. And I'll add, since quantum gates preserve the number of qubits, I will have to think ahead of time if I need working space for doing the computation later. And whatever working space I need, I will add in the beginning as a working space. So these are the zeros. And so my circuits look like that. And one qubit here is designated as the output qubit. Okay, so now I can define BQP with error epsilon over a certain universal set of gates, just like BPP. Okay? It's going to be exactly the same thing, but with quantum circuits. A language, L, is in BQP with error epsilon and a universal set of gates, G, if there exists a sequence of such quantum circuits like this, whose size grows polynomially within, such that for all x, for all input x, which is classical here, if x is in the language, then the probability that this guy here at the output will be measured to be 1, that probability is at least 1 minus epsilon. Whereas if x is not in the language, that probability is at most epsilon. Okay? And again, uniformity, which we don't care about. Okay? So that's BQP. BQP is the class. BQP is for us, since you've arrived from, since you've made the effort to come here, we are going to pretend as if quantum computers exist. So for us, quantum BQP is the class of problems that are tractable. In a world where a quantum computer exists, these are the problems that can be solved efficiently. That's BQP. Okay, I should say that, first of all, we basically saw the argument why G, the universal set of gates, does not matter here. We can choose any universal set of gates. We also basically saw the argument of why epsilon doesn't matter, as long as epsilon is bounded away from half and at least exponential, essentially by repetition. But in order to actually make these arguments more exact, we need to work a little bit more before lunch. Hang on just a little bit. Okay, so we're going to claim that if epsilon is bounded away from half, epsilon can be made exponentially small. And once we argue this, we would be able to argue more formally that the class does not depend on which universal set. Okay, and then we would have defined rigorously what's the class BQP without dependence on epsilon or universal sets. Okay, So some basic results, yeah.
Can you return to the previous slide? What does it mean Qn equal 1? It's a measurement operators?
This is sort of a very sloppy way to say I've applied Qn of x as a quantum circuit. I measured and the output was 1.
On one?
On the first qubit.
Okay, and it doesn't contain measurements during circuit?
Yes, and it doesn't contain measurement during circuits. And the reason we can do that is exactly because of the principle of delayed measurements. Even if you have measurements in the middle, you can actually apply this principle and delay them till the end.
Okay, thank you.
Okay, great. So now some basic results about BQP, which we need. First of all, BQP is at least as powerful as classical computation. We at least want that, right? Why is that true? Well, this is easy. You start from, if you have a function that can be computed by a classical circuit with S gates, you can also compute it by a quantum circuit with S gates if the quantum circuit is allowed to use NOT, CNOT, and another gate which is like CNOT except it controls not on the first or leftmost bit, but on the leftmost 2 bits. So it can be written as ABC goes to AB, C XOR AB. And notice that if C is 0, then what's written on the right here is an AND gate. So NOT is just the unitary version of a NOT gate. AND can be replaced by a Toffoli gate, which is unitary. And if C is initiated to 0, then the rightmost bit will just contain the AND gate. But this is a unitary version. So we can replace all the gates in this classical circuit by unitary gates. And of the same number, S gates. Each gate is replaced by another gate. So then that means that we got a quantum unitary circuit that computes exactly the same function. Okay? Is that clear? Or are you dozing away already? Is this clear? No, I see that it's not clear, but I'm sorry? Why did I need CNOT? I actually don't need CNOT. Toffoli and NOT is good enough. Thank you. I'm sorry? That's true. In fact, I can only have Toffoli, but at least so that we feel comfortable, we also have the NOT. Okay. So P is in BQP. I should say that in the exercise, we'll see something very important, that not only we can do the computation like that, which gives us garbage here, because we've made all our gates reversible, and then there is garbage during this transformation. Sometimes we need to get rid of this garbage, just like we've seen before in the principle of delayed measurement. When we copy a bit to the side, it actually has an effect, even though it's just copying. So garbage could actually destroy interference patterns. So if we want to actually make sure that our interference patterns are saved, we need to actually get rid of the garbage, and this is called clean computation, which says that actually this computation can be done without any garbage. And this can be done, you'll see this in the exercise. That's P. BPP. What about BPP? Actually, same thing. You start from a randomized circuit, and you make it reversible, unitary, that is, by adding these zeros, and everything is now unitary versions of Toffoli and NOT gates. And the only thing that's missing in order to show that this is a quantum circuit, there's something missing. Can you see? Yes?
How do you get the uniformly random bits?
Yeah, how do you get the uniformly random bits? That's exactly the point. And the answer, as you were about to say, is you can generate a uniformly random bit by Hadamard on 0 and then measure. But we don't want to measure in the middle because it's a quantum circuit, it's unitary. We'll use the principle of delayed measurement, and so instead of measuring this, we'll add a qubit, apply a CNOT, and everything will look like it was measured. So that's BPP contained in BQP. Good. So why BQP does not depend on epsilon and G. Now we can argue this very quickly and easily. First of all, using all that we have done so far, we can do error amplification in BQP as well, reducing the error exponentially. How? Exactly like in the classical case and using what we have done. We want to start from epsilon, which is bounded away from half. We repeat polynomially and take the majority of the outcomes. So we repeat polynomially many quantum circuits, and then apply a majority computation here, and that will be the output. To do that, we need the fact that P is contained in BQP so that the majority can actually be computed unitarily. So this majority is computed using Toffoli and NOT gates. And therefore, by Chernoff, just like before, we get exponential reduction of the error. That's the error reduction for BQP. And, well, it seems like we have used measurements before we applied the majority, but again, we can apply the principle of delayed measurements, and we don't need the measurements in the middle. Okay. You need to say something in order to argue more rigorously why the universal set of gates really doesn't matter. And maybe I'll just mention one thing about it. I won't go through the argument. That the point is that when you change a universal set of gates to another, you add a little bit to the error, right? Because of the approximation. So what you need is you need to do the amplification in order to get rid of what you've added. But amplification requires Toffoli and NOT, etc. And these gates might not be in your gate set. So what you do is a little trick. You just reduce the error before you replace by the other gate set. First you reduce the error. You start from a circuit with error epsilon. You first reduce the error, and then you get a circuit with Toffoli and etc., but with error which is smaller, and then you approximate that new circuit by gates from the universal set of gates. You add a little bit to the error, but not more than you started from. Okay, so you can. This is an easy argument. You can do it on your own later. So I want to summarize. How powerful is BQP? That's the topic of the next talk. Basically, there are lots of algorithms that can be done in BQP. We'll see some of them. We'll talk about some of them during the course. And the thing is that some of these algorithms, actually the algorithms that we'll be talking about, provide exponential speedups over all known classical algorithms. So these are examples for problems that are in BQP, but not known to be in BPP. And so, why doesn't it work? And so, if I look at the computational map now, I have BQP and BPP, and we strongly think that BQP is larger than BPP. And so this seems to violate the extended Church-Turing thesis that we talked about earlier. And so we somehow need to change, well, okay, the fact that it violates it relies on A, the mathematical conjecture that BQP is really different than BPP, and B, that we can actually implement BQP in the lab. The second one sort of relies on handling errors and noise, and that will be a topic of Sergey's talk later on. And believing that, we somehow need to change our extended Church-Turing thesis, since what we now think is feasible are quantum computations in polynomial time and not classical computations, and they are not equivalent. So we will sort of replace our extended Church-Turing thesis by a quantum extended Church-Turing thesis, which says that all physically realizable computational models can be simulated polynomial time by quantum computers. And so this gives a different notion of universal quantum evolutions, that those that are possible to do in polynomial time by quantum systems. Okay, let's go to lunch. Do we want some questions?
So we're a bit over time, so unless there's any like super urgent question. Okay, let's recess until I believe 2.
Yeah.